Hi, this is GANGADHAR, lecturer in mathematics from Giraj Government College, Nizamabad. So now today's topic is BSC second year in the real analysis infinite series. Series. So series means 1 plus 2 plus 3 plus 4 plus 5 so on. It is called a series. So let define the series. So let UN be sequence of real numbers and Sn equal to U1 plus U2 plus U3 plus so on plus UN and plus so on. Then sequence Sn is called infinite series. Sequence Sn is called infinite series. It is denoted by sigma n equal to 1 to infinite un or sigma un. Sigma n equal to 1 to infinite un or sigma un. So this series contains infinite terms. So sigma un means u1 plus u2 plus u3 plus so on plus un plus so on. So here s1 equal to u1, s2 equal to u1 plus u2, s3 equal to u1 plus u2 plus u3, so on. Sn equal to u1 plus u2 plus u3 plus so on plus un. So this sequence Sn is called nth partial sum of the series. Nth partial sum of the series. So Sn is called nth partial sum of the series. So in the sigma un we define u1, u2 so on un and s1, s2 so on Sn. Un is called nth term of the series. Un is called nth term of the series and Sn is called nth partial sum of the series. Sn is called nth partial sum of the series. So for example, sigma n cube. Sigma n cube means, so here terms are start from n equal to 1 to so on up to infinite. So first term 1 cube plus second term 2 cube plus third term 3 cube. So here we write summation of. Summation of means sum of the terms. Summation of means sum of the terms. So sum of sigma un means sum of infinite terms of un. Sum of infinite terms of un. So here sigma n cube means 1 cube plus 2 cube plus 3 cube plus 4 cube plus so on. So sigma 1 by n square. Next example is sigma 1 by n square. So here also we write n equal to 1, 2, 3 so on values. First n equal to 1, then 1 plus n equal to 2. 1 by 2 square means 1 by 4. Next n equal to 3 means 1 by 3 square. That is 1 by 9. So now the series is sigma 1 plus 1 by 4 plus 1 by 9 plus so on. So now convergence of series. So how series is convergence? So we know convergence of sequence. So convergence of sequence models are first limit sequence is bounded and it has only one limit point. Then we say that sequence is convergent. This is first one. Second one is every Montan sequence is convergent if and only if it is bounded. Second one. Third one, a sequence is convergent if and only if it is Cauchy sequence. So here we know. So convergent of sequence. So now convergence of series. So convergence of series definition is let sigma un be series of real numbers with partial sums. Let sigma un be series of real numbers with the partial sums. So Sn equal to u1 plus u2 plus so on plus un. So for all n belongs to Z plus. If the sequence Sn converges to S, then sigma un series also converges to S. So if the sequence Sn converges to S, then sigma un series also converges to S. So convergence of series definition is, first sigma un is a series and Sn is its nth partial sum. Sn is its series nth partial term, nth partial sums. So now if nth partial sum of the sequence Sn is convergent, then we say that series is convergent. Nth partial sum of the series Sn sequence is convergent, then we say that series also convergent. So it is the convergence of the series definition. So now divergence of the series. Divergence of the series. If the series is not convergent, then we say that it is divergent. If the series sigma un is not convergent, then we say that it is divergent. So now here one theorem, a necessary condition for convergence, a necessary condition for convergence. So if sigma un series is convergent, then limit un equal to 0. If sigma un series is convergent, then limit un equal to 0. So it is the necessary condition for convergence. Sigma un series is convergent, then limit un equal to 0. So now this is sigma, we know sigma 1 by n square series is convergent. Sigma 1 by n square series is convergent, since limit n tends to infinity 1 by n square equal to 0. So limit value 0. Next example, sigma cos 1 by n square. Sigma cos 1 by n square. So is not convergent. Because limit n tends to infinity cos 1 by n square. So cos 1 by n square means that value cos 0 value 1. So here series is not convergent, since limit value 1 it not equal to 0. Limit value 1 not equal to 0. So now one theorem. So if sigma an converges, then limit n tends to infinity an equal to 0. If sigma an converges, then limit n tends to infinity an equal to 0. So first proof. First sigma an is convergent. Sigma an is convergent means here we define its nth partial sum. Say Sn. Nth partial sum of the series is say Sn. So now sigma an convergence means here a limit exists. So now we will take limit n tends to infinity Sn equal to L. Then Sn minus 1 limit also L. So if limit of sequence is unique, so Sn limit is L, then Sn minus 1 limit also L. So now we subtract each from another. Sn minus 1. Limit n tends to infinity Sn minus 1. So that equal to L minus L equal to 0. So now we write Sn minus 1 nth partial sums. Sn minus 1 nth partial sums means Sn nth partial sum value. Sn nth partial sum value a1 plus a2 plus a0 start from 0. a0 plus a1 plus a2 plus so on plus an. Sn minus 1 nth partial sum values are a0 plus a1 plus up to an minus 1. So here a0, a1, a2 so on an minus 1 plus an minus a0, a1, a2 so on an minus 1 up to n minus 1 terms are cancelled. So we get only an value, an. So now limit n tends to infinity an equal to 0. So in the previous limit n tends to infinity Sn minus 1 equal to 0 we know. and Sn minus 1 value we get an. So we say that limit n tends to infinity an equal to 0. So therefore sigma an series is convergent, then limit n tends to infinity an equal to 0. So here converse of the statement need not be true. Converse of the statement need not be true. If sigma limit value 0 but sigma an not equal to not convergent. If limit un equal to 0 or an equal to 0, then sigma an or sigma un series are not convergent or need not be convergent. So now if limit un not equal 0, then sigma un diverges. So an example, so sigma n by n plus 1, sigma n by n plus 1. So here limit of the series un equal to un not equal 0, then sigma un diverges. So un equal to limit of the series is 1. Limit not equal to 0, then we say that sigma un is diverges. So another one example. So here limit sigma 1 by n series, sigma 1 by n series, that series is divergent but limit value 0. Sigma 1 by n series divergence but limit value 0. So now p test. So it is also called auxiliary series. P test, or it is also called auxiliary series. So statement of p test or auxiliary series is the series sigma 1 by n power p is convergent if p greater than 1, and it is divergent if p less than or equal to 1. So any series of the form 1 by 1 to the power p plus 1 by 2 power p plus 1 by 3 power p plus so on plus 1 by n power p, 1 by n power p, and here p belongs to R, p is any real number, then that series is convergent if p value greater than 1. That series form is, that series is convergent if p greater than 1, and that type series is divergent if p less than or equal to 1. So sigma 1 by n power p series convergent if p greater than 1, and sigma 1 by n power p series is divergent if p less than or equal to 1. So now we will see some examples here. So now first example is sigma 1 by n. So sigma 1 by n. So sigma 1 by n, sigma 1 by n first, sigma 1 by n. Sigma 1 by n means this series we write in sigma 1 by n power p form. So p equal to 1. So p equal to 1 means by p test we say that sigma 1 by n is divergent. Sigma 1 by n is divergent. So next example, sigma 1 by root n. Sigma 1 by root n. So sigma 1 by n power 1 by 2. Sigma 1 by n power 1 by 2. P equal to 1 by 2. 1 by 2 is less than 1. 1 by 2 is less than 1 means by p test sigma 1 by root n is divergent. Next, sigma n square. Sigma n square value we write sigma 1 by n power minus 2. Sigma 1 by n power minus 2. So here p value minus 2 less than 1. P value minus 2 less than 1. So we'll say that sigma n square series is divergent. So next example, sigma 1 by n power 3 by 2. N power 3 by 2. Next, sigma 1 by n square. Sigma 1 by n cube. So here p values are, one is 3 by 2, another one is 2, another one is 3. So these values are greater than 1. These values are greater than 1. So by p test we say that these type series are convergent. 1 by sigma 1 by n power 3 by 2. N power 3 by 2 value we write n root n also. Next, sigma 1 by n square. Next sigma 1 by n cube. So these type series are convergent by p test since p greater than 1. So next one, p value minus 1, sigma p value when p value minus 1, this one is less than 0. So less than 1, minus 1 means less than 1, that series also divergent. P value minus 1 by 2, so that's sigma root n. Sigma root n means 1 by sigma 1 by n power minus 1 by 2, less than 1 means series divergent. Another one, sigma 1 by n into n power 1 by 100, n into n power 1 by 100. So here power values 1 plus 1 by 100 means 101 by 100, 101 by 100. So its value greater than 1. So we say that this series is convergent by p test, convergent by p test. So another one problem, sigma 1 by n power pi, sigma 1 by n power pi. So pi value we know that 3.17 so on. So it is greater than 1. So we say that the series is convergent. Series is convergent by p test. So now geometric series. Geometric series. Geometric series. So here the series of the form sigma a into r to the power n or sigma r to the power n type series is called a geometric series. So here r less than 1, then geometric series is convergent, and r greater than or equal to 1, then geometric series is divergent. Here the geometric series sigma a into r to the power n is convergent if r less than 1. If r less than 1, series is convergent, and it is divergent if r greater than or equal to 1. R greater than or equal to 1, then geometric series is divergent. R greater than or equal to 1, then geometric series is divergent. R less than 1, then geometric series is convergent. So now we will see example. So sigma 1 by 2 power n. Sigma 1 by 2 power n means that value we write 1 by 2 whole power n. 1 by 2 whole power n. So here r value 1 by 2 less than 1. R value 1 by 2 less than 1. So by geometric series we say that it is convergent. Next, sigma 3 power n. 3 power n means r equal to 3 greater than 1. Greater than 1 means series is divergent. R value greater than 1, then geometric series is divergent. Next, sigma 1 means r to the power 1 to the power n, r value 1. So sigma r equal to 1, then series is divergent. Then series is divergent. So now series of positive terms. So now the definition, series of positive terms. So in the series all terms are positive, then we say that series is called a series of positive terms. So a series sigma un is said to be series of positive terms if un greater than 0 for all n belongs to z plus. A series sigma un is said to be series of positive terms if un greater than 0 for all n belongs to z plus. So now comparison test for convergence. Comparison test for convergence. So now this test definition is, first if sigma un and sigma vn are two series of positive terms such that if sigma un and sigma vn are two series of positive terms such that first condition un less than or equal to vn or un less than or equal to k into vn for all n greater than or equal to m. Second condition, sigma vn is convergent, then sigma un also convergent. So here sigma un and sigma vn are two series of positive terms such that un less than or equal to vn, first condition. Second condition, sigma vn is convergent, then sigma un also convergent. So now comparison test for convergence. First, sigma un comma sigma vn are two series of positive terms such that un less than or equal to vn, first condition. Second condition, sigma vn is convergent, then sigma un also convergent. So it is comparison test for convergent. So now proof of this theorem, proof of this test is, first we define nth partial sum of sigma un and sigma vn. So sigma un nth partial sum say Sn, sigma vn nth partial sum we say Tn. So Sn equal to u1 plus u2 plus so on plus un. Tn equal to v1 plus v2 plus so on plus vn. So now Sn for all n greater than or equal to m, for all n greater than or equal to m, Sn equal to, we write u1 plus u2 plus so on um minus 1 plus um plus 1 so on un. So now which is less than or equal to, u1 plus u2 plus so on plus um minus 1 plus k into vm plus vm minus 1 plus so on vn. Since Sn is less than or equal to kvn, Sn is less than or equal to k into vn. Here since Sn is less than or equal to k into vn, so vn values we write to vm plus vm minus 1 plus so on plus vn. So here, so first um plus u2, u1 plus u2 plus so on plus um minus 1. So this value we say that a, that value we say that a plus k into, so Tn minus of remaining values, so we will take Tn minus of v1 plus v2 plus so on plus vn minus 1. So here we define or we say u1 plus u2 plus so on plus um minus 1 is a, and v1 plus v2 plus so on vm minus 1 value we say that b. So here it is less than or equal to, Sn is less than or equal to, here we get a minus kb plus k into Tn, a minus kb plus k into Tn. So here if sigma vn is convergent, then sigma Tn, so what is its nth partial sum Tn? So Tn is convergent, so series is convergent, then its nth partial sum also convergent. If nth partial sum is convergent, then sequence is bounded. Nth partial sum is convergent, then sequence is bounded. So now by boundedness definition, so 0 less than or equal to Sn less than or equal to a minus kb plus kn. By boundedness definition we write, we know already Sn less than or equal to a minus kb plus ktn. So limit value Tn, limit value less than or equal to L we will take. So 0 less than or equal to Sn less than or equal to a minus kb plus kn. So here L dash by maximum of S1, S2 so on Sm minus 1 comma a minus kb plus kl, then Sn less than or equal to L dash. Sn less than or equal to L dash means, so L dash is upper bound of sequence Sn. L dash is upper bound of sequence Sn. So we say that sequence Sn is bounded above. Sequence Sn is bounded above. So in the series, so here sigma un is series of positive terms. Series of positive terms means it is increasing sequence. Sigma un is series of positive terms means it is increasing sequence, and its nth partial sum is Sn. Nth partial sum is Sn. So sequence Sn also increasing. Sequence Sn also increasing. So therefore sequence Sn is increasing and bounded above, increasing and bounded above. So therefore we say that sequence Sn is convergent. Sequence Sn is convergent. So that implies if sequence Sn is convergent, then we say that sigma un series also convergent. Sequence Sn is convergent, then we say that sigma un series also convergent. So now therefore comparison test for convergence definition: sigma un sigma vn are two series of positive terms such that first condition un less than or equal to vn or un less than or equal to kvn. Second condition, sigma vn is convergent, then sigma un also convergent. So now another test, limit comparison test. Limit comparison test. So here this test definition, limit comparison test definition. So if sigma un and sigma vn are two series of positive terms. So if sigma un and sigma vn are two series of positive terms and limit n tends to infinity un by vn equal to k not equal to 0. Limit n tends to infinity un by vn equal to k not equal to 0. Then sigma un comma sigma vn are both convergent or divergent together. So then sigma un comma sigma vn are both convergent or divergent together. So here sigma un comma sigma vn be two series of positive terms such that limit n tends to infinity un by vn equal to l, limit value not equal 0. Then test definition: sigma un comma sigma vn are both convergent or divergent together. So now example. So test for convergence of the series sigma 2n minus 1 by n into n plus 1 into n plus 2. Sigma 2n minus 1 by n into n plus 1 into n plus 2. So we verify the series is convergent or divergent. So first we define un. So un is 2n minus 1 by n into n plus 1 into n plus 2. So we know convergence of series. First, so nth partial sum of series is convergent, then we say that sigma n series is convergent. First one. Second, so p test sigma 1 by n power p. So p greater than 1 series convergent, p less than or equal to 1 series divergent. So third, geometric series. Here it is the form sigma r to the power n form. Sigma r to the power n form. R less than 1 series convergent, r greater than or equal to 1 series divergent. So next, comparison test for convergence. So here we define two series sigma n comma sigma vn are series of two positive terms and un less than or equal to vn comma sigma vn is convergent, then we say that sigma un also convergent. It is comparison test for convergent. So in the previous limit comparison test, here also sigma un sigma vn are two series of positive terms and limit n tends to infinity un by vn equal to l and l value not equal 0, then both the series are either convergent or divergent together. So now here un is the form 2n minus 1 by n into n plus 1 into n plus 2. First we find limit of un. So limit un equal to limit 2n minus 1 by n into n plus 1 into n plus 2. So in the numerator n common and the denominator 3 n's are there. So 1n cancel, 1 by n square into something. 1 by n square into something means that un limit value 0. Here we apply limit comparison test. Limit comparison test means we want a limit value not equal 0. We want limit value not equal to 0. So here 1 by n square is there. So 1 by n square into something means we get limit value not equal to 0. We get limit value 0. 1 by n square into something limit value is 0. But we want limit value not equal 0 means if 1 by n square is not there, 1 by n square is not there, then we get limit value not equal 0. 1 by n square is not there, then we get limit value not equal to 0. So we say that 1 by n square value is Vn. So we choose Vn value 1 by n square. We choose Vn value 1 by n square and we find the limit Un by Vn and we find the limit Un by Vn. So we get that limit value is 2 minus 0 by 1 plus 0 into 1 plus 0. So we get limit value 2. We get limit value 2 not equal to 0. So limit Un by Vn value 2 not equal to 0. So next Un is less than or equal to Vn. It is okay. We choose 1 by Vn. Vn equal to 1 by n square. So Un less than or equal to Vn. So next sigma Vn equal to sigma 1 by n square. Sigma Vn equal to sigma 1 by n square. Here we apply P test. So by P test, sigma 1 by n square series is convergent. By P test, sigma 1 by n square series is convergent. So now therefore, comparison test for convergent, sigma Vn series is convergent, then sigma Un series also convergent. So in the next problem, so 1 plus test for the convergence of both two series. So 1 plus 4 by 5 plus 6 by 10 plus so on, 2n by n square plus 1, it is one problem. Another one, so 1 into 2 by 3 into 4 into 5 plus 2 into 3 by 4 into 5 into 6 plus 3 into 4 by 5 into 6 into 7 plus so on. So here we know some series 1, 2, 3, 4 so on values are there. So last term is n. 1, 2, 3, 4 so on n. Suppose 2, start from 2. 2, 3, 4 so on means n plus 1. 3, 4, 5, 6 so on means n plus 2. Suppose we write even terms 2, 4, 6, 8 so on. 2, 4, 6, 8 so on are even values. So what is the last value here? 2n is the last value. 2, 4, 6, 8 so on, last term is 2n. Next we start from 4. 4, 6, 8 so on, 2n plus 2. Next odd terms 1, 3, 5, 7 so on. 1, 3, 5, 7 so on. These values are odd terms. So odd term is, we know 2n minus 1 is odd term. So 1, 3, 5, 7 so on, last term is 2n minus 1. Suppose the 3, 5, 7 so on terms are there. So last term is 2n plus 1, 2n plus 1. So in the first problem, nth term is given 2n by n square plus 1, 2n by n square plus 1. So here also we find limit of un. So 2n by n square means 1 by n into 0, 1 by n into something, 1 by n into something value, limit value 0. But if we apply limit comparison test, then we want limit value not equal to 0. So if 1 by n is not there, then we get limit value not equal to 0. So we choose 1 by n value is Vn. We choose 1 by n value is Vn. So now sigma Vn is 1 by n. So 1 by n is divergent by P test. 1 by n is divergent by P test and we find the limit value Un by Vn limit value. that value we get 2. That value we get 2. So limit value 2 not equal to 0 condition. Next un less than or equal to vn, it is okay. Next sigma vn is divergent. So therefore we say that sigma un is divergent. Sigma un is divergent. So here un greater than or equal to vn. The value un greater than or equal to 2n by n square plus is greater than 1 by n square. 2n by n square plus 1 is greater than 1 by n square. So un greater than vn and sigma vn divergent. So therefore we say that sigma un is divergent. Sigma given series is divergent. So now next problem 1, 2, 3. So here 1 into 2, 1, 2 by 3, 4, 5, 2, 3 by 4, 5, 6, so on. So first terms in the numerator, first terms are all first terms 1, 2, 3, so on. 1, 2, 3, so on means we write that value n. Next second terms numerator are 2, 3, 4, so on. 2, 3, 4, so on means n plus 1. That value we write n plus 1. In the denominator, first terms are start from 3. 3, 4, 5, so on means n plus 2. Next second terms in the denominator 4, 5, 6, so on means n plus 3. Third terms in the denominator are 5, 6, 7, so on means n plus 4. Total nth term is n into n plus 1 by n plus 2 into n plus 3 into n plus 4. n into n plus 1 by n plus 2 into n plus 3 into n plus 4. It is the nth term of the series. So now un. So we find the limit of un. n into n plus 1 means n square by, in the denominator, n plus 2 into n plus 3 into n plus 4 means n cube. N square by n cube means 1 by n into something. 1 by n into something means, so 1 by n limit value 0. 0 into something value 0. So here we want limit value not equal 0 means 1 by, we remove 1 by n. So that value we say that vn. So now here un greater than vn. So un greater than vn and sigma vn equal to sigma 1 by n. un greater than vn and sigma vn equal to sigma 1 by n. Sigma 1 by n series is divergent by p test. Sigma 1 by n series is divergent by p test. So therefore sigma un is divergent. Therefore sigma un is divergent. So now next problem, test for convergence of sigma n equal to 1 to infinite 1 by 2 power n plus 3 power n. 1 by 2 power n plus 3 power n. So here also un value 1 by 2 power n plus 3 power n. 1 by 2 power n plus 3 power n. So now we find a limit un. We find a limit un. What is limit un value? So 1 by 2 power n plus 3 power n is there means, so in the n tends to infinity limits we will take highest power of n term is common. Highest power of n term is common. So here we have two terms. One is 2 power n and another one is 3 power n. One is 2 power n, another one is 3 power n. Suppose we will take 3 power n is common. 3 power n is common. So 2 by 3 we get 2 by 3 whole power n plus 1. 2 by 3 whole power n plus 1. So 2 by 3 whole power n means values 2 by 3 first term, 2 by 3 whole square second term, 2 by 3 whole cube, so on. This way these terms are decreasing. 2 by 3 comma 2 by 3 whole square comma 2 by 3 whole cube means these terms are decreasing. If n tends to infinity, 2 by 3 whole power n tends to 0. N tends to infinity, then 2 by 3 whole power n value tends to 0. So we want tends to 0 value, limit value tends 0 value we want. So here 3 power n is common in un. So 3 power n is common. 1 by 3 power n into 2 by 3 whole power n plus 1. So 1 by 3 power n limit value 0. 0 into something value we get 0. But we want a limit value not equal to 0. Means we will take what is Vn value here? 1 by 3 power n. So we choose Vn equal to 1 by 3 power n. We choose Vn equal to 1 by 3 power n. So now we find Un by Vn limit. We find Un by Vn limit. That value we get 1. 1 by 1 plus 0 equal to 1, not equal 0. So here sigma Vn equal to sigma 1 by 3 power n. So sigma 1 by 3 power n value we write 1 by 3 whole power n. 1 by 3 whole power n. 1 by 3 whole power n. So r equal to 1 by 3 less than 1. So by geometric test sigma 1 by 3 power n is convergent. By geometric test sigma 1 by 3 power n is convergent. So therefore Un by Vn limit value 1 not equal 0. Sigma Vn is convergent, then sigma Un also convergent by limit comparison test. So next problem, test for convergence of sigma tan 1 by n and sigma 1 by n sin 1 by n. Sigma tan 1 by n. So Un equal to tan 1 by n. So here we choose Vn value 1 by n. Here we get Un greater than tan 1 by n greater than 1 by n. So tan 1 by n greater than 1 by n for all n belongs to Z plus, for all n belongs to Z plus. So we say Vn value 1 by n and Un by limit value tan 1 by n by 1 by n limit value we get 1. So we know limit theta tends to 0, tan theta by theta equal to 1. So here we apply theta tends to 0, then 1 by theta tends to infinity. So limit value 1 not equal 0 and sigma Vn equal to sigma 1 by n. So it is divergent by p test since p equal to 1. So limit value 1 not equal 0, but sigma Vn is divergence by p test. So therefore sigma Un series is divergence by limit comparison test. So next problem, sigma 1 by n into sin 1 by n. So here Un value 1 by n, sin 1 by n. So which all we know that sin theta value less than or equal to 1. Mod sin theta is less than or equal to 1 always. So apply both side 1 by n into 1 by n. Already sin 1 by n less than or equal to 1. Apply 1 by n is less than 1 by, we choose Vn equal to 1 by n square. We choose Vn equal to 1 by n square. Then so we know limit sin theta by theta also 1, sin theta by theta also 1. So here 1 by n into sin 1 by n. So in the denominator we want sin theta by theta means, so 1 by n square value we want. So 1 by n cancel, then we get sin 1 by n by 1 by n. So we choose Vn equal to 1 by n square. So Un by Vn limit value sin 1 by n by 1 by n. So that equal to 1 not equal 0. Un by Vn limit value 1 not equal 0 and sigma Vn equal to sigma 1 by n square. Sigma Vn equal to sigma 1 by n square. So it is convergent by p test. Sigma 1 by n square is convergent by p test. So therefore by limit comparison test sigma Un also convergent. Sigma Un also convergent by limit comparison test. So now one more problem. Sigma root n plus 1 minus root n. Sigma root n square plus 1 minus n. So here it is the rational function. If the function is rational function, so that numerator term we rationalized numerator term, we rationalized. Next we apply limit. So here numerator term is rationalized. So root n plus 1 minus root n means, so un value root n plus 1 minus root n into root n plus 1 plus root n by root n plus 1 plus root n. So numerator root a minus b into root a plus b, that value a minus b. So we get 1 by root n plus 1 plus root n. So here root n is common, so 1 by root n. So that value we will take Vn. Take Vn equal to 1 by root n. So sigma Vn equal to sigma 1 by n power 1 by 2. So by p-test it is divergent. Next we find un by Vn limit value. That value we get 1 by 2. So therefore we say that, so un by Vn limit value 1 by 2 and sigma Vn is divergent. So by comparison test we say that sigma un is divergent. By comparison test we say that sigma un is divergent. So in the second problem also same model. So here un, we rationalize the numerator value, then we get 1 by root n square plus 1 plus n. So here n is common in the denominator, so 1 by n into something. So we choose Vn equal to 1 by n. And it is divergent by p-test. So next we find un by Vn limit value. That value we get 1 by 2 not equal to 0. Un by Vn limit value 1 by 2 not equal 0. And sigma Vn is divergent. By comparison test we say that sigma un also divergent. So same model. Next one more problem here. So test for convergence of sigma cube root of n cube plus 1 minus n. Cube root of n cube plus 1 minus n. So here un value is we rationalize. How we rationalized? Here a power 1 by 3 minus b power 1 by 3 form is there. A power 1 by 3 minus b power 1 by 3 is there. So we know a cube minus b cube formula. A cube minus b cube equal to a minus b into a square plus ab plus b square. A cube minus b cube equal to a minus b into a square plus ab plus b square. That formula here we apply. Then numerator is rationalized. Then we get 1 by, so n cube plus 1 power 2 by 3 plus n cube plus 1 power 1 by 3 plus n square. So now Vn value n power 3, n cube whole power 2 by 3 is common here. So we get 1 by n square. Vn value we choose 1 by n square. So 1 by n square is convergent by p-test. Next we find limit value. Un by Vn limit value. That value we get 1 by 3. So limit un by Vn value we get 1 by 3. So by comparison test sigma un is convergent. By comparison test sigma un is convergent. So thank you.